So welcome to day 22 of the Common Lisp series. So today we're going to do something different. I didn't know how to title this video, but I just called it Discovering Time. But let me go into details of what we're going to do. So in the last video, we saw TCP echo server. So I thought it would be fitting if we can do something with UDP and a client instead of a server in today's video, right? And so then I remembered I had a blog post which I wrote a few years back where basically I faced a problem with my system time and I dug a bit to kind of go into NTP and try to figure out setting time. So I thought we will do the same thing today, but with Common Lisp. So last time I used Python, but I'll talk about what we did, and then let's do it again in Common Lisp. So that's the concept for today's video. So the concept is simple, right? So you have a system, you have a laptop, you have a computer, and there is a date and a time set on that computer, and your system is going to keep track of it. But how do you set the time in the first place, right? How do you know what is the right time? And I'm talking about like up to the millisecond or nanosecond level accuracy, right? So we know there are standard bodies out in the world which maintain and measure time accurately. There are these scientific labs and so on. But how do you get that value, right? So when I mean, of course, the problem happened to me because my NTP was off. So we'll come down to that. But so for instance, India has the standard organization, National Physics Laboratory, and they have a nice page for showing you the real time, right? So if I go to this page, it's showing me that the time is now 12:51, Saturday, Feb 7, 2026. And so this is, I mean, I can believe this to be an accurate enough number if I don't have any other clock, right? So that's good. But how do I set that value locally, right? So, I mean, the simple thing is, I can just go there and take that millisecond and set it, but I mean, that's not the right thing, right? So the way this works in real life is by a protocol called network time protocol. And this is a standard internet thing. It's like quite old, and it's a way for machines to synchronize time from different time servers and basically keep them up to date periodically. So we don't have to go into details of the network time protocol, but let's just look at the basics and like the challenges, right? So we have a client and we have a server. So this NTP server is running out there, and that's a standards body. And if I have a request going from the client, the server will simply respond with the accurate time, right? But that's not enough, because there is also this delay of round trip that, it takes some time for the packet to go and packet to come back. So the client has to do some updates to figure out what's the actual time. But let's ignore that part for a moment, like those few milliseconds, right? And let's more worry about like doing this request, right? So last time when I was playing around with this, I found basically there are clients and there's Python libraries. For instance, there's a Python library called ntplib, and you can use it to get the time, right? But how do you do it from scratch, right? That gives you an understanding of network protocols. And it turns out actually that this NTP is a UDP protocol. So it's based on UDP, and there are some things that you do on top of UDP, right? So that's the way these kind of internet protocols are built. So we'll take this as an example today and did what I just did in that blog post. So the concept is we want to, we don't have a client, NTP client. Instead, we want to actually, participate in the protocol manually by constructing a packet, NTP packet, and sending it and receiving it back. So, I mean, there's more details. I'm not showing you everything here. But the idea is that you can go through the protocol, you can go through the RFC, for instance, which has full details about the protocol. But the gist is basically what I learned back then, a few years back, is that, NTP is based on UDP on port 123. And the concept is you send a packet, which is structured in a particular way, and you'll get the packet back with the details, with the time aspect, right? So these details are there on Wikipedia also, on other blogs also. You can check out this blog. I have taken this diagram from elsewhere. But if you just look at this diagram, because this is a very standard network programming kind of thing that you do, right? So let me go to the Wikipedia version of this diagram. I think that's a bit clearer to explain. But so this is the NTP packet header. So what you see are so basically each of this is a bit, right? So we have 8 bits here, 1 byte, and so on, right? So you have a byte here, you have a byte here, and so on. And each byte can mean different things. So there are some fields which are a full byte, like say this one. There are some fields which are 4 bytes. So let's say this root delay value, we can go to the documentation later to see what that means, but that's 4 bytes of data, which means something in the protocol. both the sender and receiver need to know that. And similarly, there are fields here which are less than a byte, right? So basically that's just one or more bits. So for instance here, as it says here, there's a leap indicator flag, which is 2 bits, which has a particular meaning. So basically, because it's 2 bits, you have like 4 values, 0, 0, 0, 1, 1, 0, 1, 1, and each of that has a particular meaning in the protocol, right? So when you send a packet, you have to encode your logic into these bits. And let's say look at the next one, the version number. So this one, so if you see here, that's 3 bits, and that is basically used to have the version number of NTP. So now, so you have a lot of fields and a lot of meaning. So if you see your reference timestamps are like 64 bits, so basically 4 bytes into 8 bytes, and the protocol header, packet header is showing you these details. So normally if you use a client, NTP client, the program does all of this for you within the under the cover. So basically you don't know all this, the packet goes, the packet comes back, it's going to extract the fields out of the packet, and then it's going to give you the actual value, right? So but here we're going to do this part manually. And this requires a bit of like experimentation and trial and error and reading documentation, but that's kind of what I did a few years back. So I have it all here. So I have the exact values and the Python version of the program. So it's much easier for me to convert this into the common Lisp version of the program, right? But just to think about the logic. So the way to do this is to figure this out is to play around and also use tools like Wireshark and Tshark to decode the packet. I'll show you a bit of that today, but just assume for the moment that I know the protocol. And it turns out if you send a single packet which has 48 bytes in it with the required fields, and you're going to get a single packet back, which is at this point obviously NTP packet. We're talking about NTP packets. So a single NTP packet back, which would be having the requested time fields. So basically what do you have to send? So what's the minimum you have to send, right? Because there are a lot of fields here, and if you like actually think about all of this, it's a lot of complexity. But from experimentation, I figured out that there are only a few things you need to send. So for instance, I just ignore the leap indicator, so I don't care about leap seconds and so on. So I'm just going to set it to 0. Then I need to set the version number, right? And I'm going to use the version number 3. Basically, that's what was there in some reference code I had seen. There is a version 4. Maybe the protocol changes a little bit. We have to see the documentation, right? And then you have the next 3 bits, which is mode. I think it's also shown here. This mode, these 3 bits. And so basically it's saying what is the packet's role, right? What are you doing there? And so basically we want to be a client, so we'll send a packet with that mode set to client. So that means we are requesting for a time from the server. Now I need a server, right? So I figured out there is a server which is being run by the same npl. So basically there is time.npl india.org. This is an NTP server, right? So basically this is not a web server or an HTTP server like this one, because this is something that you go and you see it as a human, but this is a kind of server which is an NTP server. So you need to have a client which is an NTP client talk to this NTP server. So basically we have the server. So we can, like when I use the Python library, I just use that as the destination and request, right? And then later in this blog, I've talked about how I constructed the packet and sent it from Python. But now let's look at it from Common Lisp. So the idea is simple. We have to create a UDP packet because NTP is based on UDP. And then you have to send it to that server at port 123 because that's the standard value. So I have the full code here, and I'm going to talk about this code line by line. It's actually not, it's only 13 lines. It could probably even be simplified further. So now let's look at the code thing, right? So I'm doing a connect just to make it the rest of the program easy, so that I can use the socket S again. But you don't have to do a connect. You can directly do a send in case of UDP with that destination, right? I'm just making this for ease of use. So here I'm setting the npl india org time server as the destination. You have a port 123 and the protocol is UDP, so datagram. That's it, right? That's the socket. It's actually not a connection. There's no connection, but it's not a connection. UDP is connectionless, but that's okay. We just created the socket object. We can use it again. Now I'm going to create a packet, and from the documentation, a packet is basically 48 bytes. So I'm going to just create an array of size 48, where each element is an unsigned byte with 8 bits, right? So this is like an empty array. It's all going to be 0 in the starting, and that is going to be our packet that we're going to construct and send. Now, like I showed here, really this thing we need for NTP client is very simple. It is just these three fields that we talked about. Actually, we only care about this version number and this mode, and we are simply going to like ignore the rest of the fields, right? I mean, that is wrong in terms of like the full NTP protocol. So if you see here and the algorithm I told earlier, but we're going to ignore that and we're just going to take like whatever number comes from the server, we're going to use that. So we're going to ignore all the other fields. See, I want the simplest thing that we can do here. So all I need to do is adjust the bytes in my byte array for the business logic that I want. And here we are doing something very simple. We are setting the 0th element of that array to #x1p. So this #x part is basically hexadecimal. So we're saying what follows is hexadecimal format. And we are then using 1b to basically represent the contents of the packet. So this is very standard. If you see in low-level programming in network, you use it's very standard to use hexadecimal because it's easier, it's shorter. You're not using a full raw byte to explain the byte. You're actually going to say it 4 bits at a time. So in hexadecimal you have 4 bits. So this 0001 gets encoded as one hexadecimal entity, and then 1011 is again another entity. So in this case, basically, I mean, you can do a conversion programmatically like this. So that's what I did last time. So I'm saying convert this bit array into an hexadecimal number, and that gave me 1b. And that's exactly what we are using in the program right here. I'm just using that 1b value direct. Or you could do your conversion manually. I mean, it's not very complicated. It's just 4 digits. You can just look it up. It's straightforward, right? So basically, we have set our first packet to be non-zero. And then we are simply sending that byte data using usocket socket send. So this is what we do to use usocket as a client. So in the last episode, we were using the usocket functions as a server, as a TCP server. So here, this line is basically it behaving like a UDP client. So we are doing socket send. So there is send and there is receive, and you just basically send and receive from that socket. And just send the packet data, raw data. This argument can be a string or it can be a byte array. That's what I've done. I've taken a byte array, and you have to give the length of the size, and that's 40. So basically, at this point, you have, if everything is worked right, it has sent a packet out to the NTP server, right? I mean, that is not enough. We need to actually get a packet back, and we need to like open that packet. But these first 3 lines are all that you need for sending a packet out. Now, because we have sent our packet, we're going to get a packet back. So we have to receive it. If you don't do this, it will just, I mean, you're not completing your protocol. So let's do a receive. So we have the usocket socket receive. So if you see here, you have the socket again and the buffer. So if you pass in a buffer, you can fill in data into the buffer. I'm just setting it nil, and I'm setting the expected length 48 because that's the protocol. The protocol is going to give me 48 bytes in response also. Right? And now the thing is, because I've set this to nil, the function socket receive is going to return back a new buffer which it creates with the data. Now the thing is, the challenge here is that because it's like you need to get a buffer and of course the length of the buffer, right? So the way the socket receive is written is it's actually going to return multiple values, 2 values. And in Common Lisp and in some other languages also, you have mechanisms to return multiple values. Not as a tuple, but actually multiple values. So multiple values coming from the function, and you have to take and use those values. So if you just ignore, like if you just take and set this into a field, you'll probably only get the first value. So instead, if you do multiple value bind, so just like let, so what we're saying is I'm expecting 2 values and I'm going to store them into the variables dat and len from this function, and then I want you to run the rest of the body. So this is exactly like a let formulation. And the idea is you want to receive and you're getting multiple things and you have to just destructure them. So we can look into more. You can look more into this. I don't remember if I talked about multiple values earlier. But this is a very simple way to extract those values. In our case, we're just doing a very simple thing here again. I am just checking if the received size is 48. I mean, this is just a sanity check. Of course, in real programs and real systems, you'll have to do clear checking. But in this case, I could have just dropped this. I could have assumed that everything is fine. But this is a simple example. I'm just doing an assert and seeing the length is 48. If it's not 48, that means something went wrong. Maybe you got a mangled packet, or maybe the NTP server didn't respond correctly. You know, there are a lot of things can go wrong. It's UDP after all, but it's okay. If it's 48, I mean, we're good. We have the full packet that the server sent. So now that we have the data in that DAT byte array, it's another 48 length byte array. So how do we extract data out of this, right? So this is the next challenge in front of us. If you see my blog, I talked about this earlier in Python. I used the struct library in Python, which is a way to unpack and pack data items from their native representation into bytes representation. So this is like basically like, let's say you have an integer has 4 bytes, but your integer in Python, it's kind of like a wrapper on top of those 4 bytes. It's doing other things, right? But if you want to like literally get this raw value of bytes, what do you do, right? So struct is the library there. I'm sure there are equivalent libraries in Common Lisp, but instead I wanted to do this manually. So I'm just going to manually pick out the bytes and manually process it, just so that we have a full picture. We don't have anything. We have full clarity of what we do. Now, okay, great. So I have 48 bytes, and some of those 48 bytes are going to be useful, right? So I'm just using the, if you go back to the protocol diagram, the packet header description. Basically, we have a few different timestamps here. You see there is a reference timestamp, origin timestamp, receive timestamp, transmit timestamp. And the protocol actually talks about how you're supposed to use this, right? You're supposed to take these two and subtract and add and stuff, right? But we are just going to like, ignore that and take this receive timestamp field, right? So that will be good enough for us, right? We'll just use that. But that is like 8 bytes, right? So how am I supposed to get a timestamp out of the 8 bytes? I mean, what is a timestamp, right? So there are 2 things you need to do here. One is you need to get the bytes out, but then you need to know how to read the bytes, right? And this Wikipedia page itself talks about how NTP actually encodes the timestamp in those 8 bytes. And if you see here, it says it has a 32-bit part for seconds and the 32-bit part for fractional second, right? And basically that's the way it's splitting those 8 bytes. So 8 bytes is going to split again into 4 bytes and 4 bytes with seconds and like fractional seconds. And further you see here that is actually talking about seconds from epoch. And I mean, if you're used to Linux and Unix world, you think epoch is January 1st, 1970. That's the standard thing in Unix. But here NTP actually uses a different epoch, which is January 1, 1900. So this is a different protocol, right? It's not the same. So when you see here the word epoch, we assume something, but no, it's an epoch of a different start time, right? So we have these challenges in figuring out the thing, right? Figuring out the timeout. So before I go and explain that, why don't you just run this code and show you the packet in T-Shark, right? Just so that before we decode it, just to show you that the packet is correct and the packet is gone and it's coming back and so on. So I'm just opening my terminal and I'm just going to execute it. It's not even a function. It's basically just some code snippet. And so it has run. We'll talk about this number later. But this time now I'm going to run it again. But before running it, you know what I'm going to do? I'm going to start T-Shark, which is basically a terminal version of like Wireshark. And we are saying, I want you to filter packets which match UDP port 123. So only show me those packets. And if I start it now, the thing is my computer was also running NTP in the background. So what I'll do is I'll start it, I'll send this packet, and then I will shut it, and then we can look at the packet, right? So let's start with the packet. So the capture has started, and I'm going to execute this again. And if you go back here, there is something you see here. I'm going to close it. You see that it is captured on this interface, and it has actually captured 2 packets. The outgoing client packet, so this, you see this NTP version 3 client, and the incoming packet from the server, which is NTP version 3 again, because we said that's the version we set. Now let's go into some more detail, right? What I'll do is I'll enable the verbose mode in T# so that we're getting a lot more data, and I'm going to run this thing again. So that ran, and something is here. I'm going to cut it so that we can examine this output freely. You see there's a lot of output. If you've not seen T-Shark before, this can be overwhelming. This is the same format in Wireshark. If you're new to networking in general, I'd recommend Wireshark because you have a UI and you can filter and do things more cleanly. If you're experienced, this is enough for you because all the information is there here. Okay, so basically what it has captured is the first. So essentially we captured two packets. So this is the first packet that you're seeing here, and because networking is a hierarchical protocol, there is layers to the networking packet. So if I will start from the bottom because that's like more clear to you. So you'll see this NTP protocol, NTP time protocol. It's mentioning that as the payload. So basically there was a packet, the innermost of which was an NTP protocol, the client protocol. This is what we sent first, and you see here all of these values are 0 or null because we set the byte array to 0, right? So that's because we had an empty array here and we only set the first fields. So if I go back here, you'll be able to see this T-Shark is opening the packet, and because it has knowledge of the protocol, it's actually opening out the bits and explaining those bits to us. So you see here this exact thing that I talked about, the first two bits of this first byte, that's a leap indicator, 0. This next 3 bits, so 0, 1, 1 is the version number, and then the next 3 bits after that is the client. So this is the NTP packet, but it's basically wrapped, it's inside a UDP packet, right? And that is represented in this portion. So if you see this here is talking about that the fact that there is a UDP packet that we sent. So that's what we did in our program. We chose a destination port of 123 because that's the standard NTP so destination, and it's talking about other fields in UDP standard fields like checksum and timestamp and so on, right? This is going to be standard for any UDP protocol, so not just NTP. And finally, you have a UDP payload, which is the actual heart of this packet, which is the NTP protocol packet, and that's the 48 bytes that we sent. So you see here, actually, this whole packet is 90 bytes, but only 48 bytes are this NTP part, and the rest of it is the things about it. And of course, UDP can't just go on its own, right? So UDP is an IP protocol, so it's go on top of IP, and this is talking about my source IP and the destination IP of the NTP server and other fields in that, right? And see, if you see here, interestingly, it's actually talking about the destination because I gave the the standard time servers IP. It is, I mean, I didn't give the IP, I gave the domain name, and then that got resolved to the IP. But it's actually picking out the latitude and longitude of the destination because that server actually supports it, apparently. And I didn't go to Google and try to look it up. And funnily, it is actually somewhere in the middle of nowhere. It's in Delhi. So that part is like matching. But in Delhi, this latitude longitude like takes me to like bit of like trees in the middle of a park in the middle of Delhi. I don't know. I don't know what's going on there. Maybe that number is not accurate. Now, that is the IP part, but if you go up, you are going to get the even lower levels packet parts, right? So the other things, it's going over Wi-Fi, so this is the lower level protocol part. And so this was the packet that we sent, and then there is a frame 2, which is the packet that we received back, and that is the packet which is again 90 bytes. And if you see, it has the outer layers, it has an Ethernet frame, it has the IP frame, and it has the UDP frame inside that, and then finally it has the NTP response coming from the server. And I want you to see here the difference. Basically, this portion that is coming back is 0x1c, it seems, because it didn't do anything with the leap indicator of the version number, but it has sent the mode of the packet as server, right, which is good. It's what we expected. And there are the other fields which was there in the packet that is documented. I also don't know all the details of each of these fields, but the one that I am interested in is these fields, which is the receive timestamp and the transmit timestamp, because that's what is coming from the server. This is what I am sending, but this is what is coming back from the server, right? And so this is the number we want, right? So we want to extract this time the way T-Shark has extracted it out of the packet. We want to extract this out of the packet that we have got in our common disk script. So we have the raw data here, right? But what do we do? So to finally do this, you need one or two more things. So let's talk about that, and that is endianness, right? So the very first thing is I need to like pick out the bytes, and the bytes are, back to my protocol diagram. So you see here, it's very clear from this documentation that the bytes are actually in this range. It's actually from 32 to 40. But like we said, there are 4 bytes which represent the fractional portion and 4 bytes which represent the actual number of seconds. So we are going to only take the useful part, right? We are going to ignore the fractional part again. I mean, it's too tiny. Let's ignore that. Let's only look at the non-fractional part, right? So basically, in these 8 bytes, we only need 4 bytes, the first 4 bytes, and that's how it says in the documentation also. So this is where we are getting this information from, right? But we have a problem, and that problem is like, how do we read the bytes, right? So, and this is where we have the concept of endianness. So I'll just open the Wikipedia page if you are not aware of this concept. So there are only like 2 major protocols here, but the idea is, how do you send your bytes, in which order do you send your bytes in terms of the significant bit? So do you send the most significant bit first, or do you send the least significant bit first, right? So that you have two basically fields, such as little endian and big endian. And so your computer could be one of these two, depending on various things. So my computer is little endian, which means in my computer, in Common Lisp, if there is bytes in that order, I can convert that into a integer and expect it to work, right? But the network might not send it in the same order. Actually, there is a network endianness. So if you see here, basically RFCs can say what it is, what is the endianness of like different protocols. But in general, the network protocols are big endian, right? If it's not like specified, if it's not changed. So basically we have a problem already, in the sense that the order in which I expect, or Common Lisp expects, or my computer expects, is not going to match the order in that packet, right? So in the case of Python here, I basically used that struct library which did that thing automatically for me, right? So basically it just, I had to do exclamatory mark I, and that exclamatory mark means that use the network order, and I means use unsigned integer, because there is a difference in the bytes for signed and unsigned also, correct? But now we need to do that part manually. Not much of a problem. But now you might have a question about the byte also, right? Because you're talking about 4 bytes, but then what about each byte? So what happens is, the network protocol is actually big endian across bytes, but within bytes it's actually little endian. This can be a bit confusing, but if you just like try it out and print out the packets, it will start kind of making sense. So what it means is, an individual byte you can kind of deal normally on this machine, but when you have multiple bytes, you need to worry about the order. So because we have a big endian network order, the first byte of the 4 bytes, the byte at 32, is actually the most significant digit, right? But actually that kind of suits me, because I want to convert those 4 bytes into a single number, which you can think as an integer, right? So I'll explain this loop. So what I want to do at the end of the loop is, I want to get back the time seconds from starting of epoch, right? But that is a single integer, right? And how am I going to do this? I'm going to start the value with p equal to 0, and then I'm going to build this byte by byte, digit by digit. And because the first digit is actually the most significant one, I'm going to take that and I'm going to basically move it, add it, and then move it to the left. So, I mean, this is a standard pattern that you might have seen to say parse integers from strings. So if you have a string 1, 2, 3 and you want to get the number, the integer 123, if you take the number 1, you then take 1, and then when you read 2, you basically multiply 1 into 10 plus 2, right? And then 12 into 10 plus 3, right? And that will give you 123, right? So in the same way, I am just doing a bit shift. So what you see here is, this ASH is a standard built in to do bit shift. So I am taking the current number value, I'm shifting it left by 8, I'm going to add the new part in the rightmost, right? Because I'm just adding the two numbers, the other number will have the other bits anyway set to 0. So those two things will kind of fall together. So when I have 2 digits and then I have a third digit, I'm going to move those 16 bits to the left and add the next one. So that logic is what is happening in this loop. And that logic works as it is because the packet is a network packet. That's why it's big endian. That's why it's in that order. If it was not, you will have to reverse the thing and basically get the value. So we can do one more thing. We can see these raw bytes here because I'm just printing the array. So this is also another interesting thing. So we have the RB, which is a subsequence of the array. So basically that's 4 elements of the array. But if you see, I'm using tilde x, which means I'm asking it to print it in hexadecimal form, right? And the percentage, tilde percentage just for the new line, so that it's very clear. And you see here, actually, you can see that that byte array has been printed in hexadecimal. So it's ED318395. If you didn't do that, you probably get it in integer probably, right? Now the thing is, you can use T-shark with the -x flag to print out the hexadecimal content of the packet in hexadecimal. So I have done that just right here, and you can see that this is the output for the last second packet, which is from the server, right? And I mean, this is the decoded version, which is being decoded by T-shark itself, but this is the raw bytes which we get in our common Lisp program. So actually, if you see here, 32 to 36, the thing we have extracted here, this thing, ED to 95, you can actually see that here, right? So basically, this is a byte. So I mean, this is like the whole 90 bytes. So if you start counting from back, you'll see this is like 4 bytes, and then 4 more bytes, so 10 bytes here, right? And this portion, so 2 more bytes, 12 bytes. So basically this portion, right? And you see it's the same 4 bytes, ED31, 83, 95, which you see here, right? See, of course, it repeats, right? So like we saw the format, the next 4 bytes are going to be the fractional portion. So this is going to be the fractional portion of seconds. If you want, we can decode it. And then this is the next one, the transmit timestamp. So that's these 4 bytes. And that is it's the same as this, right? Because the time it took between receiving and transmitting, the time it took to process there on the server was very less. It was within that 1 second gap. I mean, you see here, right? The fractional portion is different. I mean, you can see it here also. This is 15 and this is like 22, so it's different, but the non-fractional portion is the same because the server was faster. Okay, so the point is, you have seen the bytes and I am doing this processing to multiply it and get the bytes in integer form. So I'm finally going to print that number in a normal form, so that ns is normal integer and we're going to print this, and we want to compare it against our current system time, right? Because now my system is right, it's running in the right time schedule. So now the number should match. But there is one more thing here, one final thing in this video, and then we are done. And that secret thing is, basically when I did this in Python, I had to add, if you see here, this is the thing, right? I unpacked those 4 bytes and then I had to subtract this big magic number, 220 so on, to get the actual answer. And why is that? Because like we said earlier, this number that is coming in NTP is the number of seconds since 1900. But we want it from since 1970 because that's the thing we are used to, right? I mean, if you normally print in any Unix tool and date and Python and so on, the time is counted as epoch from 1970. So that's why I need to add subtract. This is basically the 70 years in seconds. So this is the full 70-year period from 1900 to 1970, but in seconds. And we're just subtracting that number to match. Now I thought I had to do the same thing here in Common Lisp because in Common Lisp we have this get universal time method to basically get our current time, right? Again, I assume this is going to be seconds since epoch, but what happened was I found that I didn't have to do the subtraction. You see the number here, you'll see, look, the number is off by 1 second because when it ran and because of that. But you see in the previous times we run, it's exactly the same. It's okay. But the fun thing is that number of seconds since 1990 is the same thing that is being reported by Common Lisp. It's a bit of a surprising twist. I tried searching documentation, but I couldn't really get anything that kind of clearly documented why this is the case. You see the hyperspec for Common Lisp, and you see that the universal time, according to Common Lisp definition, this get universal time I used is something that returns a single integer, number of seconds at midnight, January 1, 1900. It doesn't, I mean, it's talking about 1900 as it's a standard. So I don't know, I don't know what's the history behind this. If you know, let me know in the comments, or in future I'll look this up. Just a cursory search, I couldn't find anything. I mean, of course, Lisp is older than Unix, but Common Lisp is younger, right? So I don't really know what happened. Maybe Common Lisp kind of took existing Lisp convention from some older Lisps, and maybe that's why that was a standard. I don't know. Again, if you know, let me know. So this is the final piece in this whole story. So basically, what have we done today? I have recreated what I have done in a blog which I had a few years back, where we are interacting with the NTP server by manually crafting packets. Instead of using an NTP client, we are doing manual packet mangling, both for the sending and the receiving. And in today's video, we have done this exact same thing in Common Lisp. In doing that, we have seen how a UDP client works. We have seen how byte array is managed and how to manipulate byte arrays. And we have also seen this universal time and the interesting twist behind it. That's it for today's video. See you. Bye.